So again, this is chapter 29, problem number 4. We're asked, what is the longest wavelength electromagnetic radiation that can eject a photoelectron from silver, given that the binding energy is 4.73 eV? Is this in the visible range? So it seems like they've left out some information, because the photoelectric effect has a specific equation that we use for it. We have kinetic energy of the photoelectrons that are ejected is equal to the energy of the incoming light, H times F, minus the binding energy, which is how tightly glued you are to whatever piece of metal you're being ejected from. Now when they ask, what is the longest wavelength electromagnetic radiation that can eject a photoelectron, that means they want to know what's the weakest energy that you can shoot at this to get an electron to actually eject. Okay? By it being the weakest energy, that's meaning you're going to find the limit. You're going to find when it doesn't eject, and then anything that has a wavelength that's less than that will actually eject. Okay? So that means that you're finding the case where there actually is no kinetic energy. So when it asks you for the maximum wavelength, that means you're saying that the kinetic energy is 0 if finding the maximum wavelength for ejection. So that helps us out. That tells us 0 is equal to H times F minus the binding energy. So then we also know H times F is equal to that binding energy. So I just did algebra to move the binding energy over to the other side. Add binding energy. H times F equals the binding energy. And I'm looking for wavelength. I don't have wavelength in here. How can I get wavelength in here? Do we see any way to get wavelength into here? So we know that frequency is the same thing as speed of light divided by wavelength. So I can do H times C divided by lambda equals my binding energy. Now I want to get lambda by itself, so I can solve for lambda. So I'm going to multiply both sides by lambda. It's going to cancel my lambdas on the left, and I end up with H times C equals binding energy times lambda. Still want to get lambda by itself, so I'm going to divide both sides by the binding energy. And I'm going to get the binding energy to cancel out. So the wavelength is H times C divided by the binding energy. So now we can plug and chug some numbers in. H, we know what that is. That's a constant, it'd be given. So lambda equals H, which is 6.63 times 10 to the negative 24. C is the speed of light. What's the speed of light? Do you remember that? 3 times 10 to the 8th. Perfect. Meters per second. And then we're going to divide by the binding energy. But they gave us a binding energy in this weird unit, 4.73 electron volts. Is that the unit I want to use? It's binding energy. What unit do I want for energies? Right, we pretty much always use SI unit. What's the SI unit for energy? Joules. So we want to convert that to joule. There's a conversion factor. 1.6 times 10 to the negative 19 joules per electron volt. So plug and chug these numbers into your calculator and let's see what you get. I want to make sure your calculators are giving the right answers. They all got the same thing at this table, it sounds like. Almost.
It's okay. 2006. Did you do?
We all got the same answer? We all got the same answer?
I did. I messed up.
Uh-oh. How about our last table? You got the same answers? No. Okay, what should we have gotten? What did this table get?
2,628.
Did you get this?
Oh.
It's 2.63 times 10 to the negative 7.
Oh. Interesting. Good, actually. Really fun.
Wait, you got
My only weird there are no weird ones.
Let me look at something. So you all got the right magnitude. You just didn't get the right exponent. So let's check this and see if maybe there's a typo in my answer. So we're off by factors of 10. So when you're off by factors of 10, because you all got the same number, right? So off by factors of 10, is there anywhere that I messed up? 4.73, that was the electron volts we were given, right? Yeah? So that's fine. 1.6 times 10 to the negative 19, that's the charge on an electron, which is the conversion between joules and EVs. That is definitely the speed of light. This is h, this is Planck's constant. So do me a favor, look up Planck's constant. I might have read this number wrong. The solutions might have had the wrong number on it.
Oh.
Planck's constant.
To the negative 34.
Negative 34. Plug into the negative 34. This is why I should cancel class on Mucinex.
I read it.
So now we got 2.63 times 10 to the negative 7 meters. Which is 263 nanometers. So make sure we're getting that. Never trust my answers.
Yeah, I do. I never had it.
So like I put two parentheses like down here and started to.
Oh yeah, go crazy
And then
with parentheses.
put this parentheses and then this parentheses and close it.
So the second part of the question, once you get the number right by plugging in the right constants, not listening to the high on Mucinex teacher, is this visible light or not?
No.
So to know if that's visible, we need to know what are the wavelengths for visible light. What are the wavelengths for visible? 400 to 700 is visible. So that's not visible. What wavelength range would that be in? So what color is 400 nanometers? Smallest wavelength. Of the people in here, Eric knows. Claudia knows. My pants know. And my shoelaces. So blue is low wavelength. So if this is lower than blue, what's shorter than blue? Well, violet. What's shorter than violet? Shorter than violet. Ultraviolet. So this isn't the ultraviolet. So that wavelength, if you shine it on silver, it'll make photoelectrons jump and it'll give you cancer. Yay. So the reason we put 0 in, they ask for the maximum wavelength that will make electrons jump. Well, by asking for the maximum wavelength, that's kind of code for asking for the smallest energy that will result in a jump. So when you want the smallest energy that will result in a jump, you can find where there won't be any jumps, and then anything that has a wavelength smaller than that, there will be a jump. So anything smaller than 263 will result in a jump. It's all about making the photoelectron energy, which is the kinetic energy, larger than the binding energy. Okay. Any other questions? So I did hear that being discussed while you were taking the quiz. What was the photoelectric energy and that kind of thing? So in this equation, right up here, it's kind of useful to know this kinetic energy right here. That's the energy of the photoelectrons. So the electrons that are jumping, that's the energy that they have. And it's all based on the energy that you give them. So this is the light that you shine to make the electrons jump. And then this is how tightly glued they are to the metal. So if the light that you're shining doesn't have an energy that's greater than the glue, you end up with a negative kinetic energy, which means you have no energy. You're not actually moving. Okay? Any questions on that, on the photoelectric effect? Very useful. Einstein won the Nobel Prize. We use it in street lights. Daytime running lights use the photoelectric effect. Fundamental result of quantum physics.